Okay, let's continue from where we left. So we were doing the Cramer's rule. So example number 2, determine all the possible values of the parameter S such that the following linear system has a unique solution, and describe the solution set as a unique solution. So you remember the unique solution. This unique solution is actually the solution of that linear system, the solution. So how can we get the unique solution? And how can we get the unique solution when we have the S here? So what can we do to S so that we can have a unique solution? Solution of this. So we use the Cramer's rule. First of all, you need to write the coefficient matrix, which you can name this one as A, which is equal to the coefficients of these. So the first coefficient there is 3S, 5, and then 9, and then 5S. So that is the coefficient matrix. Now, what is the determinant there? So what is the determinant of this matrix? Then determinant of A equals to determinant of 3S, 5, then 9, 5S. And this is giving us 15S squared multiplied by 41, 45. Multiplied by 45. Right? And this is actually the same as 15. And then S squared. Multiply or minus. I don't know what I'm doing. So minus 3. Minus 3. Minus 3. Right. Now, what is now? So here our B is equals to 3 and then 1 and 2. Or B is 3, 2. So that is all. Now, what is A1B? So A1B. A1B is equals to you. So you replace the first column by the B. So which is the same as 3, 2, and then 5, and then 5S. 3, 2, 5. So you replace the first column by the B. Then determinant of A1B is now equals to determinant of 3, 5, 2, 5S, which is the same as 15S minus 10. And this is equal, which is similar to 5, and then S minus 2. And then S minus 2. Okay. 3 for the 5, 3 here. 3S minus 2. Then A2B is equals to you replace the vector, the second vector there by B, which will give us 3S and then 9, and here 3, 2 there. Then determinant of A2B is equals to determinant of 3S, 9, 3, 2, which is equals to 6s minus 27. This is similar to 2s minus 9. Now, we remember that the matrix AX equals to B, the matrix equation. So that is a matrix equation AX. So you can put here equation AX equals to B has a unique solution if and only if A has exactly 2 pivot positions. If you reduce it, then A, for this case, should have exactly 2 pivot positions. So pivot position should be here and A. Also, for this to have a unique solution, then that means also A is invertible. A is invertible. So therefore, means that for this to be invertible, then determinant of A is not equals to 0. Determinant of A is not equals to 0. Now then, the determinant here, which is 15, s squared minus 3, should not be equals to what? Should not be equals to 0. For us to have the unique solution, that determinant there should not be equals to 0. So it means that this s, the s here, should not be equals to plus or minus the square root of what? Square root of 3. That s should not be equals to plus or minus. Because if you can't, if you put the plus 3 here, then plus the square root of 3 here, then this will be 3, right? 3 minus 3 will give us 0. So this will be 0. If you put minus 3 and then the square, then it will also be 3. Then 3 minus 3 will be equals to 0, which is not a determinant. So it means that that will not give us a unique solution. Therefore, then when s is not equals to plus or minus 3, the linear system has a unique solution. So then x1 is equals to determinant of a1 b all over determinant of a, which is the same as 3s minus 2 divided by 15 s squared minus 3. And x2 equals to determinant of a2 b all over determinant of a, which is equals to 2s minus 9 all over 15 s squared minus 3. So for us to have the unique solution, then s should be equals to or minus 3. Plus or minus the square roots of 3. Any question? Any question? Okay, I will post the notes in. I will post this section in Moodle. Okay, let's come to the next section, which is number 2 here. This is the adjoint matrix and inverse. Adjoint matrix. Inverse matrix form. Okay, let's start from 2.1, which is the adjoint matrix. So what is an adjoint matrix? So we get this adjoint matrix from the cofactors. So if we assume that n is greater or equals to 2, then the adjoint matrix of an n by n matrix A is, we write as adjoint of A, which is equals to C11, C21, CN1, C12, C22, CN2, C13, C23, and then CN3. So you continue like that, C1N, C2N, then CNN. CNN. So that is how we write the adjoint. So the adjoint is 4 factors: C11, C21, C1N1, so C12, C22, and so how do you get the cofactors? So to get the cofactors, then Cij is the ij cofactor of A, where Cij is equals to -1 I plus j, a determinant of Aij. Determinant of Aij for I equals to 1 to up to n, and also j equals to 1 to up to n. So that is how to get the cofactors. And we have done. So you need to get C11, C21. So to get C11, we remember to get C11, you delete the first row and the first row. C21, you delete the second row and the first row. Like that. So basically, what you're doing here is you're getting C11, but you're not putting this one here. So you do the transpose. So let's see an example of this. So let's work on example number 1. Example number 3. Find the adjoint matrix of A, which is equals to 367, 0, 2, 1, then 2, 3, and 4. 2, 3, and 4. So you start by getting the cofactors. Okay, so let's get the cofactors. So I would write this one in the next page. So find if we have our A to be equals to 367, 0, 2, 1, and then 2, 3, 4. Okay, now let's get the cofactors. So let's start from C11. So C11, which is equals to deleting the first row and the first column, which is basically -1, 1 plus 1, determinant of, so you delete this and that, so determinant of 2, 1, 3, 4, which will give us what? So which will give us 5. So which will give us 5. C12 is equals to -1, 1 plus 2. So basically deleting the first row, deleting the first row and the second column, the first row and the second column. So you delete this and this. So our determinant here is 0, 1, and then 2, 4, which is giving us what? Which is giving us 2. Okay. Then C13. So C13 is equals to deleting the, so -1, and then 1 plus 3, determinant of 0, 2, and then 2, 3, which will give us what? -4, which will give us -4. So C11, C12, C13, you actually delete the first row and each of the columns. Now, let's come to the next row. C21 is the same as deleting the second row, the first column. So -1, 2 plus 1, determinant of 6, 7, 3, and 4, which we get -3. C22 equals to -1, 2 plus 2, determinant of 3, 7, and then 2, 4, which you get -2. And then C23 equals to -1, 2 plus 3, determinant of 3, 6, and then 2, 3, which we get 3 there. 3. Okay. Now, C31, you delete the second row and the third row and the first column. So -1, 3 plus 1, determinant of 6, 7, 2, 1, which you get -8. C32 equals to -1, 3 plus 2, determinant of 3, 7, and then 0, 1, which is equals to -3, and then C33 equals to -1, 3 plus 3, determinant of 3, 6, and then 0, 2, which you get 6, which you get 6. Now, what is the adjoint? So the adjoint of A equals to, so using this formula here, C11, C21, so it is C11, C21, C31, C12, C22, C32, and then C13, C23, and then C33, C33. Okay. So to easily get these, then what you do, you take this one to be, the first row. So you take this to be the first row. So which is equals to 5 minus 3 minus 8. Then you take this one to be the second row, which is 2 minus 2 and minus 3. And then you take this one to be the third row, which is 4 minus 4, 3, and then 6. So that is how to get the adjoint. So you take this one be the first row, this be the second row. Okay. So you can arrange it like this. C11 first entry, so C11. C21. This one the first row, this one the second row, and this. Any question up to that? Okay, now, how do we get the inverse of this matrix? So how do we get the inverse? Now, to get the inverse here, then it is 2.2, the inverse of matrix, or inverse matrix formula. Now, if A is invertible, n by n matrix, then A inverse is the same as 1 all over determinant of A adjoint of A. So to get an A inverse, then is equals to 1 over A multiplied by A. Okay. Okay, let's prove this one on how to get this. And let's prove this. Okay, now since A is invertible, then that means if we let A inverse to be equals to the vectors B1, B2, all the way up to like Bn. If we let A inverse to be that, then we know that then A and then A inverse is equals to what? Is equals to the identity matrix. A inverse equals to identity matrix. So therefore, if we have this A here, and then we have our matrix A inverse, which you said is this, then multiplied by B1, B2, all the way up to Bn. And this is equals to, I. And we know I was what? The standard matrix, which is E1, E2, up to what? Up to En. So we know I is the standard matrix. And this one equals to this. Then use the using the Cramer's rule, then A Bj is equals to Ej, where J is equals to 1, 2, up to N. 1, 2, up to N. Then Bj are the solution. So Bj is the solution, which is a vector B1, B2, up to Bn. So those are the vectors. So those are the solution for that. So this Bj is just similar to X. So it's just similar to X. On what you were doing last time. So this is like X1, X2, X3. So we use Bj. So then this Bj is the unique solution. So this is the unique solution of Ax equals to Ej. Ax equals to Ej. So therefore, when you use the Cramer's rule, then this solution that we get from here, which is Bij, is equals to determinant of Ai Ej all over determinant of A, which is equals to -1 j plus 1 or j plus I, determinant of A ji all over determinant of A. And this is the same as Cji all over determinant of A. Okay. So Bij is just the same as, now you come and place where there was Bij, you put Ej, which is coming from here. So the way we did in council. So then, if you remember the cofactors formula, then this is our cofactor. So therefore, the cofactor is, we get it from deleting the j and I here. That's what we get. So the cofactor is a scalar, which you get from here. And then divide by what? Determinant of A. Determinant of A. So then, therefore, our A inverse is the same as B11, B12, B1n, B21, B22, B2n, all the way to Bn1, Bn2, Bnn. And these are the solutions that we get from here. So those are the solutions that we get from here. So you get B11 there. So then this is equals to C11 all over determinant of A, C21 all over determinant of A, all the way to Cn1 all over determinant of A. And then you continue like that. C1n all over determinant of A, C2n all over determinant of A. And then you continue like that, Cn n all over determinant of A. And this will basically give us, so you factor out the determinant, 1 all over determinant of A adjoint of A. So therefore, what you need to do is you get the adjoint and then you divide by what? 1 over determinant. That is what we get, the A inverse. The A inverse. Now let's get the A inverse from example number 4. So example 4. Now use the inverse matrix formula to find inverse matrix of A, which is equals to 3, 6, 7, 0, 2, 1, 2, 3, 4. So we have already found the adjoint here. So the adjoint of A equals to 5 minus 3 minus 8, 2 minus 2 minus 3 minus 4, 3, and 6. So we found the adjoint. So what we need to do is we just need to get the determinant. So determinant of A is equals to determinant of 3, 6, 7, 0, 2, 1, and then 2, 3, and 4. So we already have the cofactors that we already solved. So we just use the cofactors. So you can use the second row here. So this is the same as 0, which is 0. The next one is 2 multiplied by C22 plus 1 multiplied by C. We are deleting the second and then 3. C23. And we already have it here. So C22 is equals to minus 2 multiplied by 2 plus 1 multiplied by C23, which we found as 3. And this is equals to minus 4 plus 3, which is giving us minus 4. So therefore, A inverse equals to 1 over determinant of adjoint of A, which is equals to 1 all over minus 1. 5 minus 3 minus 8, 2 minus 2 minus 3, and then minus 4, 3, and 6, which is the same as minus 5, 3, 8, minus 2, 2, 3, 4, minus 3, and minus 6. So you distribute the negatives there. Any question? Any question? Okay, you don't have any question, then let's go to the next chapter, just chapter 4. We'll start from 4.1, and this is the vector space and subspaces. The vector spaces and subspaces. So we will start from the first one, which is the vector spaces. The vector spaces. So let's start from 1.1 definition. So what is a vector space? So a vector space is a non-empty set. We can name this one as capital V, on which there are two operations. We have two operations, which is the addition and scalar multiplication, which is the addition, whereby if we have the U, vector U plus the vector V, for U and V, which are in the capital V. U and V. And scalar multiplication, which is CU for U in capital V, and C, which is an element of real number. And this is subjected to the following axioms. So for it to be a vector space, then it must satisfy it axiom C. So a vector space is a non-empty set on which there are two operations. We have two operations. It's a vector addition and scalar multiplication. So for this to be a vector space, then there are 8 axioms that it must satisfy. So the first one is commutativity. So if we have two vectors, which is U plus V, then if you add U plus V, it is similar to adding V plus U for all U and V are in capital V. So that is commutativity. So you can add U plus V, which is similar to adding V plus C. Number 2, associativity. We have 3 vectors, U plus V plus W is equals to U plus V plus W. Then these 2 vectors here can be added together, and then you add the W there. Or this is similar to adding V plus W, and then you add. And this one is for any U, V, and W. which are us in V, or are in the whole vector space. Number 3, there is an element which is a zero vector, which you can say this one is a zero vector in V, such that U plus the zero vector, you still get U. U plus zero vector, you get U for any U element in the capital V. Number 3, or number 4, for each U which is in V, there is an element V, which is the negative vector of U, which is a negative vector of U in V, such that U plus V equals to 0 vector. So if V is the negative vector in U of U, then if you add the two vectors, then it is giving us the zero vector. Number 5, if you have the scalar C and then you have the vectors U plus V, then you can actually distribute that scalar in each one of the vectors here. So CU plus CV for U V in capital V and C element of real. Number 6, if we have two scalars D and then you have a vector of U, is similar to CU plus DU for U element of V, and C and D are real numbers. Number 7, we have C and D U, then it is the same as C and D U. If you can multiply D and U, and then you come and multiply the other scalar C, which is similar to multiplying the two scalars here, and then you multiply by the vector for C and D element of real number and U in the capital V. And then finally, number 8, the identity, if you multiply the identity, which is 1 multiplied by U, it is the same as getting a U for U in the capital. So those are the 8 axioms that must be satisfied for it to be called a vector space. So those are the main, or the 8 axioms to be satisfied. So every element in a vector space V is called a vector in V. It's called So let's do some 3 remarks here. We have some remarks here. So remark. Number 1. Every vector V has a unique 0 vector. Every vector V has a unique 0 vector. So let's see the proof here. Now, suppose that 0, 1 and 0, 2 are 0 vectors in V, whereby, if you remember axiom number 3, then U plus 0 vector is the same as what? If you take U plus 0, 1, it is the same as U. And also U plus 0, 2 is the same as what? Is the same as U. The same as U. For any U in one. So then 0, 1, 0, 1. So 0, 1. So 0, 1. That's 0, 1. Then you can actually check this one to the other side. Right? So 0, 1, you can check this to the other side. So basically 0, 1 is equals to 0, 1 plus 0, 2. And this is the same as 0, 2 plus 0, 1, which is equals to 0, 2. So it shows that it is unique. So if you check this the other side, so bring them here, then you distribute, you know that U can also be 0, 2, then put it like this, then basically 0, 1 is the same as 0, 1 plus 0, 2, 0, 2 plus 0, 1 is equals to 0, 2. So it shows that 0 vectors are unique. Remark number 2. Every vector U in V has a unique negative vector, which is denoted negative U, negative U. So we can meet on Friday. So I'll post these notes in Moodle.